Hi, I'm Maurice Dupre, and in this section we're going to discuss the derivative as a rate of change. Let's look at how we define the instantaneous rate of change of a function in general. The instantaneous rate of change of f with respect to x at the point x naught is the derivative f prime at x naught, which of course by definition is the limit as h approaches 0 of f at x naught plus h minus f of x naught divided by h, provided the limit exists. In other words, we think of the derivative of a general function at x naught as being the instantaneous rate of change of that function. Well, let's look at a special case, the case where the function tells us position. In that case, we think of the instantaneous rate of change as what's often called the instantaneous velocity. So if s equals f of t gives the position at time t of some moving point or particle, then the derivative in this case, the instantaneous rate of change of s with respect to t, or the derivative of f with respect to t, gives us what we call the instantaneous velocity. And in fact, I've put parenthesis around instantaneous because in general, when we say velocity, that's what we mean is the instantaneous velocity at a particular instant. So the velocity at any time t is ds dt, which is f prime of t, and of course that's the limit as delta t approaches 0 of delta s over delta t. In more specifics, that's the limit as delta t approaches 0 of f of t plus delta t minus f of t divided by delta t. So that gives us our velocity. Now, often in everyday language, we speak of velocity and speed interchangeably, but the reality is velocity and speed are technically two different things. So in physics and in mathematics, when we use the term speed, what we mean is the absolute value of the velocity. So that would be the absolute value of ds dt. That is, the difference between velocity and speed is that in this case, the velocity could be negative, and that would indicate that the position is decreasing as a function of time. That is, when we think of the position as being specified by a numerical coordinate on an axis, to say that the velocity is negative would be to say that we're moving in the direction of negative numbers, that is, in the negative direction along the axis. So consequently, remember that velocity includes the notion of direction as well as speed. Well, we can see that the derivative is very useful for analyzing motion because, for instance, when we know the position as a function of time, the derivative gives us the velocity as a function of time. When we analyze motion, we also need to consider often acceleration. Let's look to see how that's defined. Acceleration. If s equal f of t equals position at time t, then by definition the acceleration a at time t is the derivative of the velocity at time t. Of course, the velocity, remember, is the derivative of position at time t, so consequently dv dt is the second derivative of s with respect to t. If I go ahead and differentiate one more time, I get what's often called jerk. J of t is dA dt equals the third derivative of position with respect to time. And this quantity, the rate of change of acceleration, is often called control. For instance, think what happens when you're driving your car in a straight line in a direction. You control the acceleration of the car by changing your foot's position on the accelerator pedal or pushing harder or less hard on the brake. And so by doing that, you're controlling the acceleration. When you need to come to a stop in a hurry, you accelerate quickly, whereas if you need to come to a stop slowly, you just push on the brake gently. So the rate of change of acceleration is really how you control something by changing the acceleration. And it's often called jerk because in some applications it's done by using quick changes or jerks. Let's use derivatives to analyze a body's motion. Particle motion. At time t, the position of a body moving along the s-axis is s equal t cubed minus 6t squared plus 9t meters. A, find the body's acceleration each time the velocity is 0. B, find the body's speed each time the acceleration is 0. C, find the total distance traveled by the body from t equals 0 to t equals 2. Now, let me just point out a couple of things about what we'll most easily do to solve this problem. We're going to be needing velocity. We're going to need acceleration. We're going to need speed, which is the absolute value of velocity. So consequently, the first thing to do will be to take the derivative of this function to get the velocity and then differentiate again to get the acceleration. Once we've got those functions, then we can look at them to see where the velocity is 0, where the acceleration is 0, put the resulting times, for instance in part A, into the velocity function to find the velocity where the acceleration is 0, put the resulting time where the acceleration is 0 into the velocity and take the absolute value to get the speed. And then finding the total distance will be a little trickier, and so let's begin work. So I've written the expression down here that we have to work with, s equal t cubed minus 6t squared plus 9t. So the velocity v is the first derivative, 3t squared minus 12t plus 9. And we're going to be interested in where velocity is 0, so let's factor that expression. We have a common factor of 3 in each term, so we have 3 times t squared minus 4t plus 3. And of course, that's simply easily factored now. T minus 1 times t minus 3. Notice the cross terms, and negative t and negative 3t adds up to negative 4t, whereas negative 1 times negative 3 is plus 3. So there's our velocity, and there's its factorization. Now we differentiate again to get the acceleration as a function of time. So the derivative of 3t squared is 6t minus 12t. Its derivative is negative 12. And the derivative of a constant is 0. So now we have the very simple expression 6t minus 12. Again, we're going to be interested in where is the acceleration 0. So let's factor that. It's so easy. Factor out the 6 and we get t minus 2. So look at this. We see the velocity is 0 at t equals 1 and t equals 3. Those are two specific times, and we want to find what's the acceleration when the velocity is 0. So those are two times. What are the values here at t equals 1 and t equals 3? So a of 1 is 6 times 1 minus 2. That's negative 6 meters per second squared. And how about at t equals 3? 3 minus 2 is plus 1. So a at 3 is plus 6 meters per second squared. Now, where is the acceleration 0? Well, the acceleration is obviously 0 at t equals 2. So now we need to find the speed here at t equals 2. So let's look at our velocity at t equals 2. What happens? 2 minus 1 is plus 1. 2 minus 3 is negative 1. Plus 1 times negative 1 is negative 1 times 3 is negative 3. So v at 2 is negative 3 meters per second. And so what's the speed? The speed is the absolute value of negative 3, which is 3 meters per second. So there we've found our accelerations when the velocity is 0, and we've found our speed when the acceleration is 0. Now the last thing we have to do is find the total distance that this particle moved. Here's the trick. Notice we want to calculate the distance from t equals 0 to t equals 2. So from t equals 0 to t equals 2, how far did we go? If I were to take, remember our function is s equals t cubed minus 6t squared plus 9t. If I were to take that expression and just take s at time 2 and subtract s at time 0, I would not get the distance that we traveled. I would get the net distance that we traveled. Or I should say, really, more accurately, the net change of position. Notice this could be 0 if s at 2 equals s at 0, so there'd be no net change in position, or it could be negative if s of 2 is a positive number which is bigger than s of 0 is a positive number which is bigger than s of 2. So that's just the net change in position, but when we ask for distance traveled, we have to take into account which way we went and how far in each direction. Now, remember our velocity function, v of t, we factored, and it was very easily seen to be 3 times the quantity t minus 1 times the quantity t minus 3. So what's its value at t equals 0? At t equals 0, we get -1 times -3 is +3 times 3 is 9 meters per second. So at t equals 0, the velocity is positive, and then as t increases, notice this factor right here, as it gets to be slightly positive, a positive number -1 is still negative, but when it gets to 1 and passes 1, this factor will turn to positive. Positive times negative will then be negative, and the velocity is changing sign. That is, what we've done is we've moved in the positive direction from t equals 0 to t equals 1, and then from t equals 1 to t equals 2, we're moving back in the negative direction. And so what we want is the net change from t equals 0 to t equals 1. That would be s of 1 minus s of 0. We want that distance, and then plus the absolute value of s of 2 minus s of 1. In other words, we want the sum of those two distances traveled. And when we compute the difference s of 2 minus s of 1 and take the absolute value, and s of 2 minus s of 1 and take the absolute value, this works out to 6 meters, whereas if we simply take the change in position, we would think that it was only 2 meters. Let's look at a problem where we use our theory of derivatives to solve a problem in calculating acceleration on a small planet. Explorers on a small airless planet used a spring gun to launch a ball bearing vertically upward from the surface at a launch velocity of 15 meters per second. Because the acceleration of gravity at the planet's surface was g sub s meters per second squared, the explorers expected the ball bearing to reach a height of s equal 15t minus 1/2 g sub s t squared meters t seconds later. So in other words, here is the expression for the position at time t, provided that g sub s is the acceleration of gravity on this planet. The ball bearing reached its maximum height 20 seconds after being launched. What was the value of g sub s? In other words, here our theory in effect will tell us that that is the expression for position as a function of t. And so by using this measurement of when the ball reached maximum height, we can then find what the acceleration of gravity is on this planet. Well, let's take the basic information here. S equals 15 minus 1/2 g sub s t squared, and the maximum height is reached at t equals 20 seconds. Well, one of the things you may have observed is that whenever you throw a ball up in the air, at the instant it reaches maximum height, it appears to stop. In other words, a typical flight of an object launched versus time, if it goes straight up, its path as position on the vertical axis versus time is a parabola, and that's what that expression is. It's clearly a parabola opening downwards because the coefficient of t squared is negative. So we see from this picture that right there at maximum height, the tangent line is horizontal, and of course the slope of the tangent line is telling us the velocity. And so consequently, we want to find that relationship between the time at maximum height and the position and the velocity. Well, to get the velocity, we just differentiate. V is 15, the derivative of 15t is 15, minus 1/2 g sub s times the derivative of t squared, which is 2t. Notice the 2's cancel, leaving just g sub st. So v is 15 minus g sub st. Well, what we know is that at the instant where we reach maximum height, the velocity is 0. So we put 0 equals v at the time for maximum height, that's 20, equals 15 minus g sub s times that time, which is 20. So there's our equation. 15 minus 20 g sub s equals 0. And of course that says 20 times g sub s equals 15, or g sub s is 15/20. Let's cancel here 5s, and that will leave us 3/4. Our units for distance here are meters. Our time is in seconds, so our acceleration is meters per second squared. So what we find is that the acceleration on this small airless planet due to gravity is 3/4 of a meter per second squared. We've all heard the story about Galileo dropping things from the top of the Leaning Tower of Pisa in order to demonstrate that all objects fall the same way under the influence of gravity. Whether that actually happened, I don't know, but let's analyze to see what would have happened had he done it. Had Galileo dropped a cannonball from the Tower of Pisa 179 feet above the ground, the ball's height above the ground t seconds into the fall would have been s equals 179 minus 16 t squared in feet. What would have been the ball's velocity, speed, and acceleration at time t? About how long would it have taken the ball to hit the ground? What would have been the ball's velocity at the moment of impact? That's what we call the impact velocity. And of course, some smart aleck might always say that the ball's velocity when it hits the ground is 0 because it stops. But what we mean is, in effect, the velocity with which it hits the ground. So those are the 3 questions we want to answer here. Now, the basic information we have to go on is that S, the position at time t, is given by this simple equation, 179 minus 16 t squared feet at time t seconds. So how about the velocity, speed, and acceleration? We just differentiate. So v is ds dt. The derivative of 179 is 0. It's just a constant, minus 16 times 2t. So that's negative 32t, and that's in feet per second. How about the speed? That is the absolute value of the velocity, and of course, we're taking the t to be positive here, starting from time 0 when the cannonball is dropped. And so consequently, the absolute value of negative 32t will simply be 32t feet per second. And then as far as the acceleration is concerned, that's just the derivative of velocity. And so if I differentiate negative 32t with respect to time, all I get is the constant coefficient there, negative 32, and that's in feet per second squared. That is the standard acceleration of gravity on Earth here, approximately to the nearest foot, and it's fairly reasonable to use in applied problems, that the acceleration of gravity on Earth is negative 32 feet per second squared. So now let's find how long it takes to hit the ground. So back to our basic position as a function of time, s equal 179 minus 16t squared, to find how long it takes to hit the ground. Well, when it hits the ground, the position is 0. 0 equals 179 minus 16t squared, and so we just solved that for t. Well, so obviously this means 16t squared equals 179, and so t is just the square root of 179 divided by 16. And here we can take out a calculator and we'll find that's about 3.3447. That's enough decimal places. And so consequently, that is the time at which the cannonball hits the ground. Now our velocity is a function of time. Remember, v at any time t, it was the derivative of this, which was negative 32t. And so consequently, to find the impact velocity, all I do is substitute this time at which the ball hits the ground back into the velocity function. So the impact velocity is simply v at square root 179 over 16, which is negative 32 times the square root of 179 over 16. And if we calculate that with our calculator, we find that's about negative 107, give it a 0.03, and this is, of course, feet per second. So what this means is, now remember, the speed is the absolute value of velocity, so the significance of the negative sign, of course, is that the ball is going downwards. So it's going downwards at 107 feet per second when it hits the ground. When we have the graph of velocity versus time, we can look at that graph and figure out a lot of things about the motion that gives rise to that velocity diagram. Let's look at an example. Here, I have the graph of v equals f of t. Think of the velocity as being in meters per second. And so v is f of t, and of course we haven't specified what the actual form of the function is. We could work it out since it's all straight lines, but let's just look at it. V equals f of t. So that's a graph of velocity versus time. And we want to consider what that tells us. So the accompanying figure shows the velocity v equals ds dt equals f of t in meters per second of a body moving along a coordinate axis. When does the body reverse direction? When approximately is the body moving at constant speed? And what's the graph of the body's speed for 0 less than or equal to t less than or equal to 10? That's the range on which our graph was defined. And D, graph the acceleration where defined. Okay, so let's put the picture back and answer the questions. So when does the body reverse direction? Well, it reverses direction where velocity goes from positive to negative or goes from negative to positive. So notice in the interval from 0 to 2, the velocity was always positive. But at time t equals 2 seconds, the velocity turns negative. At that instant where t equals 2, the velocity is 0. If the velocity is continuous, notice that it can't change directions without going through 0. Every place we change directions will be a place where the velocity is 0. Now the velocity is going ever more negative until finally it becomes constant over the range from about t equals 3 seconds to t equals 6 seconds. There the body is moving at constant velocity, and in fact, since speed is absolute value of velocity, the speed is constant. Now at time t equals 6 seconds, the velocity, which is negative, starts increasing until finally at t equals 7 seconds, it gets back to 0 and then increases to be positive again. So right there at t equals 7 seconds is another place where we're reversing directions. So direction reversals occur at t equals 2 seconds, t equals 7 seconds. Now the velocity continues to increase until finally at t equals 8 seconds it starts decreasing again, still positive, and then at 10 seconds the velocity gets back to 0. Now, we couldn't really call this a direction reversal at t equals 10 because that's the end of our information. If it continued down in this direction, then at t equals 10 we would have had another reversal of direction, but of course it may go up in this direction, or this t equals 10 seconds may have signaled a time where the body actually ceased to exist. Maybe it went poof into thin air. So that's the way we find where the body reverses directions. If the velocity is continuous, simply look where the graph crosses the horizontal axis. Also, as far as finding where the body is moving at constant speed, we just look at places where the graph is horizontal, because that's where velocity is constant. How about the graph of the body's speed? Well, to graph speed, we just have to graph the absolute value of velocity. How do you graph the absolute value of any function? Well, you just take wherever it goes below the axis and reflect it up. So for instance, here at t equals 3 seconds, we're at -3. Instead, the speed is +3, so that would be a point. And its speed is constant from t equals 3 to t equals 6, so the speed will still be 3 over at t equals 6, and then we decrease uniformly down so that at 7 seconds we're at speed 0. So to graph that, we just simply reflect those lines upward, and that's easily done in this case because the graph is so simple. So as far as the speed is concerned, the graph goes 0 up to 3, down to 0, up to 3, stays 3 from time t equals 3 seconds to times t equal to 6 seconds, drops down to speed 0 at t equals 7 seconds, back up to speed 3 at 8 seconds, and then gradually uniformly drops down to 0 again at t equals 10 seconds. And so that's all there is to it. What about if we wanted to graph the acceleration? Remember, acceleration is the derivative of velocity, and so consequently the acceleration will not be defined at these endpoints, and it's not defined at these vertices of the graph. And so what about the acceleration during the time interval 0 less than 2, t less than 1 second here? Well, as you go from 0 to 1, the velocity increased by 3 meters per second. So the slope of that line, which is the acceleration, is 3. And so consequently, the graph of acceleration, we'd put an open circle right here at height 3 on the vertical axis, and then draw a little horizontal line and put an open circle right there at height 3 over time t equals 1. Now, from time t equals 1 to time t equals 3, the velocity is going down. The slope is now -3. Notice the symmetry here you can see is as you went from time t equals 1 to time t equals 2, the velocity decreased by 3 meters per second. So here the acceleration is -3, and it stays that way until 3 seconds. So now putting our little open circles at height -3 underneath times t equals 2 and t equals 3, we draw a horizontal line segment connecting those little open circles. And what about from time t equals 3 to time t equals 6? Remember, acceleration is derivative of velocity. Derivative of a constant is 0. So now we put our open circles right up here on the axis at times t equals 3 and times t equals 6, and we actually draw a horizontal line, which I'll thicken the axis there so you can see this. And then what about from t equals 6 to t equals 7? Notice the velocity increases again by 3 units. In other words, it went from -3 to 0. And from time t equals 7 seconds to 8 seconds, again, it increased by 3 units. So what we have is a rate of increase of velocity of 3 meters per second per second. And so consequently, our acceleration is 3 all during this interval from 6 to 8. So again, we would put open circle here, draw another horizontal line. And I'm going to thicken this to distinguish that from our previous speed graph. So these thick bars will be for the acceleration graph. And now what about from 8 seconds to 10 seconds? Notice in this case, it took a whole elapsed time of 2 seconds for the velocity to change from 3 meters per second down to 0. That's half the rate before. Of course, it's going down. So there we have negative acceleration, and that would be half of 3, which is 1.5, but it's negative, so we have -3/2. So about halfway down here, open circle underneath the 8, open circle underneath the 10, and connect those with a horizontal line. So consequently, there is our acceleration graphed as a function of time. Now, what about the derivative of acceleration, which is what we call jerk? We haven't asked about that at all, but think about it here. In this situation, the acceleration was +3 meters per second squared during the time interval from 0 to 1, and then suddenly from time 1 to 2, it's changed to -3 meters per second squared. That's quite a change of acceleration. In other words, that's a big instantaneous jerk that's occurred at time t equals 1. Whoops, I see I put the little open circle here in the wrong place. It should be back here. We have that underneath t equals 1. So there is our acceleration graph. So at t equals 1, we have an enormous jerk. Then again, at t equals 3 seconds, we have an enormous jerk, which changed the acceleration to 0. And then at t equals 6 seconds, we have an enormous sudden jerk, which changed the acceleration back up to 3 meters per second squared. And then at t equals 8 seconds, we have another enormous jerk, which changed it down to -3/2 meters per second squared. Let's look to see how we can analyze the flight of a rocket with the graph of velocity. So here we have the graph of velocity versus time. Time is in seconds on the horizontal axis, and notice we have the grid here is showing 5 minor lines to 2 seconds, and so that means each of these little segments is a 4/10 of a second interval. And so on the vertical axis, we have velocity in feet per second. So at time t equals 0, the rocket is launched and its motor is burning, and so it's accelerating upwards. Notice the slope of this velocity curve is increasing and increasing right up to that instant. So right there, acceleration is increasing, and notice the highest point on this velocity curve is right there at 190 feet per second. At that instant, t equals 2 seconds, the motor stopped burning, and notice what happens. Gravity takes over, and so the acceleration, the slope of this line segment is negative, becomes constant. Notice we have constant acceleration from t equals 2 all the way over here, t equals 10.8 seconds. And if you calculate what that represents in terms of change in velocity divided by the elapsed time, you find it's, in fact, negative 32 feet per second squared, which is the acceleration of gravity. What happened right here at this point? Well, at this point, the parachute popped out to slow the rocket's fall. And so consequently, you see what happens. Suddenly, the acceleration gets less negative. It never completely goes positive. It just slows the rocket's fall down. As far as the rocket's maximum height, remember when an object goes up, it keeps going up at its maximum height. It's going to have velocity 0. And so we look to see where is the velocity 0. That's at t equals 8 seconds. That's where the rocket reached its maximum height. Not t equals 2 seconds. That's where the rocket actually reached its maximum upward acceleration. Notice the slope of the curve right here is steeper than it is over here where the parachute popped out. So in fact, the largest acceleration was right here where the engine burnout. It was accelerating faster and faster and faster until suddenly the engine stopped. Well, we've looked at some problems of using derivatives to analyze motion. Remember, the velocity is simply the derivative of position, and acceleration is the derivative of velocity. Also, remember, when you're looking at a velocity curve, that is the graph of velocity versus time, where the velocity is 0 will indicate where you had either a maximum or a minimum in your position. Now that you've seen these problems worked, you should try some on your own.